Okay, so let me give you some guidance on problem number 2. Here's the problem, and if we put it in the matrix and try using the compute ODE, the exact solution, then if we do that, Scientific Notebook doesn't give us any result. And this actually happens fairly commonly. The algorithms that Scientific Notebook knows just are limited, and some equations can't be solved using them. And this is one example. So what we do in this case is to go for another approach, and we'll just implement the separation of variables technique that we saw earlier. So here's the differential equation, and y is the dependent variable, t is independent, and so we separate them just like so. This works pretty well to separate. We go put that over on that side, and then we have to invert it. So there's y over on that side, t comes over on this side, and b can really be on either side, but let's put it over here and it'll be 1 over b. So there's the equation separated. I'm just going to rewrite it and get rid of this fraction here. Okay. So there it's separated. We just have t and b, the constant, over on this side, and y and a constant over on this side. And so we can integrate this, and we'll do that. I guess let's do it like this. Let's do it in a couple of steps just for clarity. So we'll put the integral in here, and we'll put another integral here. So what we have is this equation, then we integrate both sides, we get that equation, and now we're going to solve these two equations separately. So that integral we can evaluate as equal to that, and this one is just the simple result we have there. And then we equate those two. So essentially we're substituting the result back into this equation. And of course we need to add the constant of integration. Okay, so that's the result of doing this separation and integration. And y is what we're trying to solve for as a function of t, but before we can do that we have to solve for the constant. So the procedure, just like last time, is to use the initial condition to solve for the constant. So there's the initial condition, and we'll do that using the substitution capabilities, where we highlight that equation, put it in square brackets, and the way we express this initial condition in a form we can substitute is we say that y equals 0 and when t equals 0. Okay, so we substitute in those two things and make it a subscript and do evaluate. And that's what C1 equals. Okay, so the procedure then is to take this result where we have it in terms of the constant and put the constant in here. So this is the result, y and t and constants. Now, what we've done with the previous problems is we've gotten the independent or the dependent variable. In the previous result, the dependent variable was L, and we got it over on the left hand side and had it be a function of the dependent variable on the right hand side. So that's great when we can do it, but in this case actually it's not going to work that way. what we'll do is simplify this, and I think we can simplify it somewhat by combining these log terms. So let's take this result, copy it, and bring the log term over on this side, like so. And then we can copy it again. And let's see, how about if we can combine the log terms, but I think before I do that, what I'm going to do is divide through by a. Okay, now actually this equation is dimensionless. That's dimensionless because the log is dimensionless. And the dimensions of y and a cancel, and the dimensions of t divided by ab cancel. Okay, so what we can do then is combine the logs, and we have log of a minus the log of a plus y, and the way those combine is like this. And now we have y's on this side and t on this side, but what we would like to do is have just y equals t. But here's the problem. We have y there, and we can't pull the y out. We can't factor a y out and combine it. So this is essentially t as a function of y. So this is called an implicit form. The result we would prefer is this, where L in this case is an explicit function of t. Here we say that y is an implicit function of t. So that's the way it goes in some cases, and this is one example of an implicit function. What we can do is we can still plot this up, and we can still use it for some applications. What I'm going to do is take that form and write it in a dimensionless form. And the dimensionless form is, I'm going to replace y with y over a, because that's dimensionless, and t, well, I'll replace with t over ab, because that's dimensionless. So let's do this. Let's call this y star. And t star. Where y star equals y divided by a, and t star equals t divided by ab. Okay, so we're almost done. What we can do now is to divide top and bottom of this log term by a, in which case that becomes 1, that becomes y over a, and that becomes 1. Well, y over a, that's just y star. So we can then change this one to put in the y star there. Okay, so now we have y star as a function of t star. The advantage of doing it is that the constants here are now embedded in the variables, and so we can plot this as y as a function of t. And what I'm going to do is use the ability of SciNotebook Notebook to plot an implicit function. So we go plot 2D and implicit, and let's see. There's the result. So this is y, the function of t, or in this case x. And we see that it loops back on itself here, so it's multi-valued. For every value of x, or in this case time, we have a value of y that's here and here. For the problem that we'll solve in class, we'll be interested just in this positive value. But the thing that I wanted to show you is that we can use SciNotebook Notebook to plot this kind of a implicit function using plot 2D implicit. Another way to plot this would be just in Excel. We could make values of y. We could make a column of values of y and then plug it in here and solve for the values of t, and then we would just reverse those columns when we plotted it. Okay, so this equation, it ends up being a little bit more involved than the previous one, and we end up with this implicit form, which is a bit different. This will be the only implicit formula that we get with the analysis that we'll be doing in class, and so I wanted to point it out to you at this point and show you how at least one way we can deal with understanding what this equation means by plotting it. When we work this problem in class, we'll put it in context. We'll have an interpretation of what we mean by y and t and so forth. Right now, of course, we're just treating it as just the basic math problem, so we don't have that context. But it'll be useful to have this under our belt, this solution method, when we do take a look at this solution, or do take a look at this analysis in